Hi, I'm Dane Quinn, and welcome to Lecture Notes for Dynamics, Engineering Mechanics. I'm at the University of Akron, and today's lecture will be an introduction to the class and the topic of dynamics. So let's go ahead and start. So what's the goal? The goal of this class, and dynamics in general, is, as we've seen here, to develop models to predict the response of a mechanical system to external effects. So if I look at some object, say B here, it might have, say, some forces applied to it, and there might be, say, some applied moments, M. So really what we'd like to do is relate the external forces and moments, so again here represented by F and M, and notice that both of these are vectors. So we'd like to relate these external effects acting on the object, which we've defined as B, to the motion of that object. So the position, velocity, and acceleration. And so why would we want to do this? Well, really engineering is ultimately about design. So engineering is about making things better, coming up with solutions, improving existing items, basically designing and redesigning systems. So how does this idea of dynamics and developing models to predict the response of mechanical systems fit in with engineering design? Because if we can do this, in particular develop models to predict the response, this allows for the design of mechanical systems under dynamic conditions. So it allows us to design mechanical systems so that the response under load, particular forces and moments, is acceptable, whatever acceptable in the context of the problem that we're interested in means. So we can sort of lay this out into a fairly nice flowchart, this engineering design process. So we'll start with a physical system. Okay, so this could be an existing design, or it could be a concept design. And from that physical system, so this is the actual thing, we would like to make a mathematical model. So we take the physical system and we will combine that with a description of the external of X, forces and moments, for example. Could be things like initial conditions as well, though. And we will formulate a model, a mathematical model that represents the physical system. And this comes with assumptions. So in order to do this, we must make assumptions about how the physical system operates. Things like spring laws, assumptions on the motion, those kinds of things. And then once we have the model, we will then go and analyze this. And we'll do so in order to make a prediction. So again, we have a physical system. We look at the external effects and we make assumptions on that physical system in order to come up with a mathematical model. And from there, we will make a prediction about how the physical system behaves. So notice that I have these boxes. This light blue box represents modeling. So the process of developing a mathematical model from a physical system. Then this purple box describes analysis. So given that mathematical model, can I solve it and predict how the model will behave? Hopefully, then predicting how the physical system will also behave. Again, there were assumptions that were made in order to develop the model, but if those assumptions are good, then the predictions from the analysis should closely approximate the actual response of the physical system. But that's not engineering design, not yet anyway, because engineering design closes this loop. Once we have a prediction, we need to determine if the performance is acceptable. So hopefully we're able to come up with some metric to determine if the performance of our system is acceptable. And so again, there actually is work to be done in determining, for example, appropriate metrics for measuring performance, given the actual response of the system. So here I evaluate, is my system behaving appropriately? Is the performance good or not? Well, if the performance is good, right, that's great, because essentially at that point we're done. So if again the answer is yes, then we can stop this process. However, if the answer is no, then we have to make changes. And this is where the design aspect comes in, because now we must modify the physical system. So we make these modifications, and we run through this process again. So this last sort of orange box is where the design comes in. So we take the predicted response, we evaluate the performance, and then if the performance is not good enough, we make modifications, and we go back and redesign the physical system. And then we step through this process again. With our new redesigned system, we'll make a model, we will evaluate the response, and we'll check the performance. If the performance is good, then we're done. But we keep iterating this loop, this engineering design loop, until we get good performance and we are done with the process. This class, Dynamics, primarily fits into this blue box, modeling. And we'll get into a little bit of analysis and predicting the response of the system, but not quite all in. Typically, the equations that we derive from the modeling are differential equations. And here in this class, we won't focus on the solution to those differential equations, but we will ask some questions about things like acceleration, maybe forces, and that sort of thing. So we'll do a little bit of analysis in this class. But for the most part, we are interested in developing models given a physical system. And here, even the physical system, we don't typically address. For example, in these video lectures, I won't be showing you, say, a car. I will show you a representation of a car that has a lot of the assumptions sort of built into them. So we'll be taking these assumptions and together with the external effects and making mathematical models, then making a few predictions about how those models behave. However, this is a pretty nice thing to know, because this is how this work and this topic in this class fits into the larger aspect of engineering design. So, on to it. How do we do this? Well, we base our models on sort of the fundamental laws of mechanics. These are commonly referred to as Newton's laws of motion, written down in the form that we know them best by Sir Isaac Newton, who lived from 1642 to 1727 in his famous textbook Principia, which was published in 1687. So these three laws, sort of written in today's modern language, can be described as the following. Law 1 says the motion of a particle is uniform, which means unchanging, unless a force is applied to that particle. Law 2 is that the time rate change of linear momentum is equal to the net force acting on the particle. And Law 3 is that for every action, there is an equal and opposite reaction. So, a little bit more about these. Law 1 defines an inertial frame of reference. And so an inertial frame of reference is one in which Law 1 holds. So in general, for engineering applications, the ground is taken to be an inertial frame of reference. So an inertial frame of reference is one that's not accelerating. Of course, the ground outside us certainly is accelerating because the Earth is spinning on its axis and spinning around the sun, and the sun is moving through the universe. And so there is acceleration of the ground, right, the dirt. But it's typically very, very small. And for most engineering problems can be neglected. There's certainly some that it can't be. But for most applications, the ground satisfies our requirements for an inertial frame of reference. Now, contrast that to, say, an example where you were in the back of a semi-trailer truck. So you didn't really have any visual reference outside, but as the truck moves, you can sometimes feel the motion of the truck, right? And not bumps over the road, but if the truck is going in a straight line and everything is smooth, you wouldn't be able to tell that the truck is moving. You have no way of knowing how fast it's going. However, if it begins to move around a curve, then suddenly you can tell that the truck is accelerating because the truck is no longer an inertial frame of reference. So those are two examples, the ground and the truck moving in uniform motion, where that frame of reference is not accelerating. But certainly the truck moving around a curve or speeding up or slowing down would be a non-inertial frame of reference. So if the motion of a particle is uniform in the absence of any applied force, then we know that we have an inertial frame of reference. So now the second law is the one that we will work with most. And this says that the sum of the forces, right, the net force acting on the particle, time rate changes are derivatives with respect to time. And linear momentum is the mass of a particle times its velocity. This we refer to as linear momentum balance. And it will serve as the basis for much of what we do in this course. There are other ways of representing this idea that we will also see later on, but linear momentum balance is where we'll start. Sum of the forces is the time rate change of linear momentum. And then the third law is that for every action there is an equal and opposite reaction. And this describes the interaction between particles. Right, so if I have two particles that are, for example, in contact, then the third law helps us to determine the forces between those two particles. Now we keep saying the word particle. Newton's laws of motion are strictly defined for a particle, an object with finite mass but infinitesimal size. So we also sometimes refer to this as a point mass. Later on in the course, we will be dealing with things that have finite size, right? So blocks and disks and rods and those kinds of things. But there's actually some work to be done to go from Newton's second law, linear momentum balance, which again is defined for a particle, to the appropriate laws defined for rigid objects. Right, so to begin with, we'll stick with a particle. In many cases, the mass of the particle is constant. There are certainly cases where we can consider things that have non-constant mass. But if the mass is constant, then this equation reduces to sum of the forces equals the mass of the particle times its acceleration. And here, the acceleration is taken with respect, once again, to inertial space. So we would be looking at, for example, the change in velocity with respect to inertial space, or the second derivative of position with respect to inertial space. Now, this entire equation often gets referred to as dynamics. So dynamics is the application of Newton's laws to mechanical systems. But we often break this up into two parts, really the left side and the right side. So the left side is referred to as kinetics. And this would be the consideration of the forces that act on the system. While the right side is referred to as the kinematics. In particular, studying the allowable acceleration for an object. So again, we take dynamics and we break it up into kinetics, which is the sum of the forces, and kinematics, which is the mass times acceleration part. So now a little bit more about that process. Dynamics, again, is the application of the laws of mechanics to develop the equations of motion that describe the response of a system to external effects. So again, taking linear momentum balance and applying that to a specific system at hand. Really, the question that we are interested in here is what motion occurs, right? What happens? I take some forces, I apply them to a system, and again, what motion does that system undergo? But we said we break dynamics up into two parts, right? One is kinematics and the second is kinetics. Kinematics, again, is the consideration of the allowable motion. And it has to be consistent with any constraints that are applied and act on the object. But it's completely without regard to the actual forces that produce the motion or the motion that actually occurs. Kinematics is not concerned with what actually happens. Kinematics is concerned with what motion could occur. So again, dynamics is about what motion occurs. Kinematics starts off by asking what motion could occur. And here I have three examples. So in the first example, this block is constrained to move on the plane. Granted, the plane is inclined, but the block can only move up and down the plane. So that constraint influences the kinematics of the system. So if I were to measure where this block is, I could get away with simply measuring the distance down the plane, because it can't move off the plane, right? It has to stay on the plane. So that's a constraint, and that influences the allowable motion. Now, contrast this case, where the block is restricted to this plane, with the second example, where this block is free to move anywhere in the plane. Right? So it could follow a path like this. Not only is it free to move anywhere, right, but it could actually spin and rotate as it goes along. So some later time it could be at a different orientation. These kinematics are very different from here. Right? So the allowable motion for this second example has much more freedom than the allowable motion for this first example. Now the final example that I'll look at is a particle that is at the end of a rigid rod. Here, the allowable motion is very different. This particle, because of the constraint induced by the rod, must remain a fixed distance from this pen joint. So once again, this constraint significantly influences the allowable motion. And I could describe the configuration of this system using only a single measurement. For example, the angle between the rod and maybe the horizontal axis. So now, if we look at these two examples, I might need one measurement here. I might just need one measurement over here because of these two constraints. In the middle case, I would actually need 3 coordinates. 2 of them would be associated with where the center of the block is, and then I could have a third coordinate that described the relative orientation of this block about the point fixed at the center. Right? So again, I could take this block, I could move it over, and I could spin it around. So that's actually 3 measurements that I would need in this unconstrained system. So again, kinematics is all about what could happen. And finally, we have kinetics, which is a description of the forces that are applied to a mechanical system. And the corresponding question is, what forces cause motion? Looking at this, if I combine kinetics, what forces cause motion, with kinematics, what motion could occur, I can answer questions about the dynamics of the system, namely, what motion actually does occur. Now, let's look in a little more detail about the kinematics of the system. While kinematics, again, is the consideration of the allowable motion of an object, the goal of this part of our solution procedure is to describe the position, velocity, and acceleration, namely the motion of an object, in terms of coordinates that specify the configuration of the system. So we'd like to define some coordinates, and ultimately, in terms of those, describe the allowable motion. So notice that I have 3 different words here highlighted. So let's look at those one at a time. And we'll start with system. Right? So when I say system, what I mean is a collection of objects. So this is everything that makes up the problem that we're interested in, the mechanical system. And down here I have an example. Right? I have a bar that's pinned to the ground. There's a spring attached to the end. Then there's a second mass that's attached by a spring to that bar at some intermediate point. So this is the system. It's the bar and the 2 springs and the constraints and the block and everything. Now, when I talk about configuration, that is the physical space that's occupied by the system. Or where are all of these different material points and objects? Where are they in space? And so the configuration, if the system is moving around with velocity and acceleration, the configuration can change in time because the physical space occupied by these elements can vary. I have shown the system in 2 different configurations. So say this is t equals t1, and this is some later time, t equals t2. So this is the same system at 2 different times occupying two different configurations. Notice that the bar is moved and the block has moved relative to the bar and with respect to the absolute position. So again, we have two different configurations for the same system. Finally, coordinates. This is probably the most important one. Coordinates are measurable quantities. So again, things that can be measured. Such as distance, or perhaps angle. In the above example, we could measure the angle between the bar and the horizontal. We could also measure the distance between the mass and the attachment point on the bar. But so these are measurable quantities that specify the configuration. They're not just measurable quantities. There are lots of things we can measure, but they are measurable quantities that specify the configuration of the system. So let's look at that in a little more detail. Again, we're looking to describe the position, velocity, and acceleration of an object in terms of coordinates that specify the configuration of the system. So here we have a bar with a spring at the end. I've essentially taken away that hanging mass just to make things a little simpler. But we want to distinguish between coordinates which are involved in the kinematics and the description of the motion, and parameters. Both of these things are measurable, but coordinates specify the configuration, while parameters do not. In particular, parameters are measured independent of the configuration. So I don't need to know where the bar is, for example, to measure the parameters of the system. Things like the mass of the bar would be independent of the configuration. The length of the bar, independent of the configuration. In contrast, coordinates, because they are used to specify the configuration, they certainly depend on the configuration. So for this example, this bar attached with a spring to the ground, let's identify and distinguish between the parameters and the coordinates. So let's look at the parameters first. Now, one thing is they're measurable, right? We can certainly measure the parameters. For this system, the parameters might be, for example, the mass of the bar or the length of the bar. Those are both quantities that I can measure independent of where the bar is. Also, the stiffness of the spring would be a parameter. The unstretched length of the spring would be a parameter. So these are all things that I can measure, but they don't specify the configuration. Now certainly they influence the dynamics, they influence the response of the system, but if I know K, I don't know where the bar is. If I know M or L or D, I don't know where the bar is. Other parameters might include gravity, right? So the gravitational constant would be a parameter of the system. Now, typically parameters are constant. Not always, but for most cases, these parameters are constant in time. They don't vary as the system moves and changes its configuration. Instead, they specify properties of the objects. So again, here in green, we have a number of different parameters. Those can be contrasted with coordinates. So coordinates are certainly measurable. Right? So both parameters and coordinates are measurable. And this is one of the things that students need to distinguish between what constitutes a parameter and what constitutes a coordinate. Because again, they're both things that you can measure. And so here, the parameters of the system might include, say, the angle of this bar, maybe theta. So if I know theta, I can tell you where the bar is. Alternatively, z, the stretch in the spring, that would be a coordinate. If I told you what the value of z was, you could tell me exactly where the bar was. So again, coordinates are measurable as are parameters, but coordinates specify the configuration. And are typically time dependent, so they vary in time. The kinematics of the system, in particular the motion of the system, is defined in terms of the coordinates. Now the last thing that we'll mention is degree of freedom. Notice that in this example, knowing theta would allow me to determine z, or knowing z would allow me to determine theta. So these two coordinates are dependent on one another. The degree of freedom is the minimum number of coordinates necessary to specify the configuration. So it's a minimum number of coordinates needed to specify the configuration. Remember, however, that the configuration encompasses all of the objects in the system. For example, on the previous slide, this system would require 2 coordinates in order to specify where everything is. For example, we might need to know the angle of this bar and then the displacement of the block relative to the horizontal line here. Again, if I knew how far down this block was and I knew the angle of the bar, I could tell you where everything is. Oftentimes, as we saw on the last slide, you can define more than one coordinate or more than one set of coordinates. Here we could define the angle and the distance between the block and the bar, or I could define the stretch in the spring and the displacement of the block. So there are lots of different choices, but ultimately we just need 2 independent measurements to describe the configuration of this system. While in this last simpler example, we only need 1. So this would be a 1 degree of freedom system. Again, it's the minimum number of coordinates needed to specify the configuration. So that's our introduction to dynamics. As we move on from here, we'll talk a little bit more about motion. We'll describe some vectors. We'll do lots of different things with the kinematics. And eventually, we will look to model the response of mechanical systems to external forces, because of course that is the goal of dynamics. So that's it for now. Thank you very much, and I look forward to seeing you again.